So we looked at the first definition of your acids and bases. So the first one that was kind of developed was by Arrhenius, and it's really just referencing concentrations of hydrogen ions or the concentration of hydroxide ions. So if we have an increase in hydrogen ions, it's known as an acid. And if we have an increase in hydroxide ions, it's known as a base. Okay. As an organic chemist, I think this definition is pretty useless because it really doesn't cover all reactions. And so when we're looking at defining species, we want to come up with a definition that applies to everything that we look at as opposed to one very narrow field. Right, so we'll expand this definition a little bit, but the last thing I want to address within it is that it becomes particularly relevant when if you move into 152. They really work with this definition as your primary focus for things that are acids or bases. So as just kind of an extra little test, let's see what happens and see if we can't determine if we're looking at an acid or a base with the compound sodium carbonate. Acid or a base. Those of you that were in lab on Tuesday might have a suggestion. What would you say on Tuesday? Where'd you get base from? Sodium is a metal, so we are looking at an ionic compound. But just because it's an ionic compound does not mean it's a base. For instance, if we look at the compound sodium chloride, that is definitely not a base. Okay, so according to our definition, for it to be a base, what do we have to have? Hydroxide, OH minus. Do we have OH minus here? No. It's kind of an odd thing to go through and say because what are we going to see in just a few seconds? This compound is actually basic. Okay? But the question becomes is how would you know that? Well, it comes back to these definitions. Okay? The idea is that you add this compound to water. In the presence of water, do we see an increase in the concentration of hydroxide or H+? That becomes a trickier aspect to go through and evaluate. Not one that you're expected to do in this class. I'm just trying to get you a preview into future places. So in this case, you would look at this compound, and according to our definitions, we'd run it as a salt because it's a metal and a nonmetal. It doesn't cleanly classify into presence of hydroxide or H+. If we expand our definition to what Arrhenius was talking about, we add this species to water. What happens? And it may be better if we rewrite the formula for water. What kind of reaction might you predict here? Double replacement sounds reasonable. So we'll exchange the cations. What do we end up with? Is that formula balanced? No. Carbonate's a -2, hydrogen's a +1. To balance that formula, we need H2CO3. Plus, what's the remaining? Sodium with OH. That being an aqueous species means that what have I increased the concentration of in solution? OH. Which then means basic compound. Okay? So in 130, we're expecting you to look at the compound and just make kind of a gut call. Yes, I see hydroxide, that is a base. Yes, I see hydrogen in front of our compound. That is an acid. When you move further into chemistry, we have to expand those definitions a little bit. This is your first expansion. We have to look at how it reacts with water. What is the end result? In this case, we form sodium hydroxide, which is a strong base. We've made a basic solution. Kind of makes sense? Okay. This is a little confusing. It's because it is kind of confusing. That's why we spend whole classes on this kind of discussion. Questions about this? Yeah?
So OH here is not a free ion? It's in a compound?
Is it a free ion? If it's aqueous, what does that mean? We've talked about it in lab. You can dissociate anything that's aqueous into the ions. You'd have sodium ion and hydroxide ion. You've increased the concentration of hydroxide by adding sodium carbonate to water.
Would the hydrogen carbonate be acidic?
So yes, this compound is technically acidic, but is H plus actually there? No. As soon as we form this, what happens to H2CO3? Turns into water and CO2. There is no H plus. Okay. So again, I think these definitions are pretty useless because it only focuses on the concentration of H plus and hydroxide. And if we expand and look at other compounds, we need to see that there's other ways we can have species act as bases and acids. So the second definition, which I feel is much more appropriate, though still also a little bit narrow, comes from Bronsted and Lowry. So what they noticed is they got similar reactions, but under different circumstances. So what they did is take the same system. If we take a look at HCl, we would define HCl as what? What is HCl defined as, according to our previous definition? An acid. And if we named it hydrochloric acid. Sodium hydroxide? Base. In Arrhenius' definition, we said we had hydroxide and we had H+. Bronsted Lowry tried to expand that definition ever so slightly. They referred to the acid as a hydrogen ion donor. So if we look at what HCl does, where's its partner? What does it look most like in the products? Well, there's our chloride. So to go from HCl to NaCl, what did that compound have to do? What did Cl minus have to do, or HCl? It had to ditch a hydrogen. It had to donate the hydrogen to some other species. Okay? So we refer to our acid as a hydrogen ion donor. Well, what did the NaOH species do? It took the hydrogen. If we look at its most similar species, we've got H2O. What's the relationship between H2O and sodium hydroxide? There's our hydroxide. What did it do? It accepted a hydrogen. That now becomes our definition for Bronsted Lowry bases. Is a hydrogen ion acceptor. Did we switch on our Arrhenius acid now becomes a Bronsted Lowry base? No. If we've defined it as an acid, it will be an acid in every single one of our definitions. If we defined it as a base, it will be a base. Okay, always. But just because it's a base in a Bronsted Lowry, or if it's a base in a Bronsted Lowry definition, it does not necessarily mean it's a base in an Arrhenius definition. Okay. So we can hide bases, okay, away from our kind of understanding. For instance, if we look at the equation HCl plus NH3, the result we get here, also known as NH4 plus Cl minus. Notice there's no hydroxide. But what happened in the course of the reaction? HCl did what? Donated or lost a hydrogen. So if it lost a hydrogen, what does that make it? An acid. What happened to the NH3? It gained a hydrogen. So according to the Arrhenius definition, it's nothing. I mixed an acid with nothing, and something happened. Well, that's a bit weird to go through and reference that. So that's where Bronsted Lowry stepped in and said, okay, well, actually, I'm going to define that as a base, but I'm going to change the definition of a base to mean a hydrogen ion acceptor. Okay? It has accepted or gained NH+. That now makes it a base. Okay? Kinda, sorta.
So, are they used both of them?
You are responsible for both of them. Depending at what level you're going into, you may need to use more or less of one or the other. The primary definition within general chemistry tends to focus on the Arrhenius definition, but you're kind of expected to understand what's happening with the Bronsted Lowry. You can usually get away under most circumstances with general chemistry with the Arrhenius definition because general chemists are stupid. Don't care about looking at the overall response. They're a little bit more focused on just getting to the numbers. If you get into the numbers, we don't care necessarily what to define them as because I don't have to predict anything. I just have to look at the numbers. What does the experiment say happened? Right. Whereas an organic chemist or a biochemist, or yeah, pretty much those two, would care more about what was happening. Right? And in that response and what's happening, we need to use the Bronsted Lowry definition more frequently than the Arrhenius definition. Okay? We started to look at some reactions here, and it helps to go through and reference things. Okay? So we're going to come up with a couple extra terms that can pop out of this. We're going to make reference to something known as a conjugate. Okay? This is going to become particularly important for this sequence of compounds. Actually, no, I changed it around to make it a little bit easier. Okay. If we take a look at this first reaction, okay, what would we predict our products to be? It's intentionally tricky. There are technically two answers. Don't worry about the one at the bottom. We'll ignore that one for the moment. So what do you mean by the one at the bottom? Maybe that'll help.
SO3 -2 and H3O.
How did you do that?
Just, I brought the, it was the donor, and it was base.
And I'm going to write it as this. Yeah, so we can see the hydrogen being bound to water. It's gained a hydrogen. Does that make sense? As opposed to H3O+. Okay. Why did you do that? Okay. Well, let's try it a different way. Couldn't I have just as easily said, with the same reactants, is that an equally valid? Yeah. This compound is an interesting compound. Why might it be interesting? In the top equation, what did it act as? We go to that species there. Single replacement means we exchange just one atom. Okay. And it's a complete swap. We aren't doing a complete swap here. Why did you say an acid?
Because it donated its hydrogen.
If we look at its beginning and its end, at the beginning it had a hydrogen. At the end, does it have a hydrogen? No. So it donated a hydrogen. If it donates a hydrogen, it's an acid. Or acidic. Sorry, I didn't mean to not use your exact wording. What happened in the bottom equation? It gained a hydrogen, which means it's a base. Well, which is it? Does it gain hydrogens or does it lose hydrogens? Either, depending on the circumstances you put it in. So this compound has the qualities of both being an acid and a base, which makes it amphoteric. Fun little word for the day. How big of a deal is that? Not really that big of a deal. But it is an extra term that can come out of this. If we take that a step further, what other compound is amphoteric?
Are the three gas formers amphoteric?
Technically, yes.
Does that have anything to do with ampho, the explosive?
I have no idea what ampho is, so I would say no.
Okay.
I'll look that up after class to see what I can come up with. What other compound is amphoteric? What did water do in the course of this reaction? In the first reaction, what had happened to it? It gained H+, which means it's a base. In the second reaction, what happened to it? It lost H+, which means it's an acid. We've talked about in a couple cases why water is super cool. All of life is based on it. One of the big reasons why water is super cool, it can also act as an acid and a base. It can facilitate the exchange of hydrogen ions back and forth depending on the environment it's located in. Is this important? Well, is respiration important? Okay. The exchange of hydrogen ions is mediated through water and other species, okay, within our bloodstream. Okay. Getting enzymes to do their job and change structures within our bodies is mediated through water because it can shift a hydrogen ion from one location to another location relatively quickly and easily. The only way it can do that is that it acts as both an acid and a base.
So could the same be said about the other compound?
The other compound could theoretically do the same thing. Okay. Quantifying that ability is the next trick to worry about, and we're only going to slightly look at the quantification aspect. Water is kind of in an optimal range to be able to do both very, very easily. The other compound here isn't so easily done. Okay. So I'm going to clear all that and see if I remember right. We said acid base. Okay. Back to our coloring. What is different about the reaction shown than we've seen in any other reaction?
Middle,
What was that?
like the arrows go back and forth.
Take a look in the middle. What's going on with those arrows? They're going both directions. Okay. Every reaction we've seen so far goes one direction. It goes towards the products and it never goes any other direction. Why? It's easier to understand if it only goes one way. Okay. What happens in this case is, in fact, all reactions tend to have an ability to be reversed. Some of them have a larger ability to be reversed than others. Okay. In this case, the reaction can be reversed. So let's look at the reverse reaction. What happens to go from SO3 minus 2 to the, on the right-hand side to the reactant side on the left-hand side? What does it become on the reactant side? Not what does it act at, what does it become? Either HSO3 minus or H2O. Does SO3 minus 2 become water? No. Okay, so it can't become water, so it's being connected to HSO3 minus. What did it act as to do that? Okay, so I just heard two terms come out of this. What changed to go from SO3 minus 2 to HSO3 minus? It gained a hydrogen. If it gains H+, what does it become? A base. What happened for the reverse reaction for our H3O+? What does it look most like in our reactant? H2O. For that reaction to occur, what happened? It lost a hydrogen, which means it was an acid. So when we look across our reaction, we can start to group things that look similar. the H2O is similar to our H3O plus. The SO3 minus 2 is similar to our HSO3 minus. Okay. And to go from reactant to product, it will act as one thing. To go from product as reactant, it will have to act as the opposite. Why would it act as the opposite? You're going the opposite direction. Okay. So we want to come up with some terminology, because if I said, what is the base in this reaction? What is your answer? Which one? Good question. We have two things labeled as bases. We have water labeled as a base, and we have SO3 minus 2 labeled as a base. So it's now an ambiguous question. You don't know which one I'm referring to. Okay. So we can change our nomenclature, or our naming of this a little bit, so that we can better reference our bases or our acids within our reaction. Okay. Most typically, what do you think I would be referring to if I said, what is the base in this reaction? Probably look at H2O, because H2O is reactant. It's on the left-hand side of our equation. Okay. Fair enough. That is kind of our standard basis. When we're looking at the reactivity or naming of species, be it an acid or a base, we tend to refer to the reactant side, or the left-hand side of the equation, because that's how we've looked at all equations. Okay. It also helps that when we read from left to right. So the first thing we encounter is the left-hand side of the equation. So how can I make sure, if I want SO3 minus 2 to be my answer, if that's what I'm going to fish for as my answer, how can I change the question so that you know that is what you're supposed to be answering? And as a sort of hint, we can make reference to our conjugate partners. Okay. Think about conjugal visits. I know that's not the greatest example. Okay. But if we have conjugal visits, you're allowing partners to come together because they have some kind of relationship. Okay. When we're looking at an equation, we have conjugate partners. They are related to each other across the reaction. So I can refer to now my blue system as my conjugate partners. The conjugate partners for the blue one would be HSO3 minus and, I already forgot the other one, SO3 minus 2. Those are now conjugate partners of each other. Okay. If we now use that term on top of our acid and base term, HSO3 minus is best referenced in this case as our acid. SO3 minus 2 is best referenced as a base, but that would be confused with H2O, so I will refer to it as the conjugate base. The word conjugate is now referencing, in most circumstances, the right-hand side of the equation, the product side of the equation. I guess right-hand side for you is this side. Okay? Kind of makes sense? So it's just a way of trying to come up with a referencing system so that if I ask acid, you tell me HSO3 minus. If I ask conjugate acid, you tell me H3O plus. So the conjugate is now on the product side. So I'm now looking at H3O plus or SO3 minus 2. Which of those two species is an acid? H3O plus. How do I know it's an acid? I look at what happens to it in the reverse reaction. And in the reverse reaction, H3O plus loses H plus. That makes it an acid. Kind of, sort of? Okay. How about in the next reaction? Whoop, I already gave you some answers there. SO3 minus 2 will, of course, have to act as a base. Why can it not act as an acid? It doesn't have any hydrogen to donate. Okay. So what would our products be? Okay. This would be a trickier one to look at. What would be our product if our sulfite anion reacts with hydronium ion? And I would accept two answers here. Say that a little bit louder. H2SO3 and okay. How did you go through and do that? Why did you say H2SO3? Okay. But if it just swaps, why'd you say H2 and not just H? SO3 minus is a -2, so you're trying to balance out the charge, right? But if we look, hydroxide came out all by itself and it came out charged. So for the reaction you just did, SO3 minus acted as a base by accepting hydrogen. How many times did it accept hydrogen? Twice, which means we did 2 reactions. Fair enough. You're allowed to do that. Let's simplify it. Do it only once. And what would our result be for the H2O, or sorry, OH minus? H2O. In this case, we've done a single acid-base reaction as opposed to 2 at a time. And if we go through and look at our reactions, H3O plus acts as an acid because it loses a hydrogen. It becomes H2O, so it lost a hydrogen in that course of that reaction. What would the conjugate acid be? HSO3. How do you know that?
That's the conjugate partner of SO3.
We know by definition our conjugates are best referenced on the product side, and you're going to hate me for that best reference segment in a second here. Okay. On our conjugate is best referenced on our product side. How do we know which one's the acid? Well, we'd go through and look at our reaction. What happens to HSO3 minus to go back to the reactant side? It has to lose that hydrogen, which means it is an acid for the reverse reaction. What happened to the H2O? It has to gain a hydrogen. So if we look at our reverse reactions, we have the conjugate acid and our conjugate base. Okay? Questions about that? I am going to throw in a hard wrinkle here that I'm not a fan of, but this is how it shows up, say, potentially in the future at some point. What? In the recent future, say probably within the next 2 weeks. Conjugate refers to the pairs. If you are asked to identify the conjugate base, okay, technically our acid and our base shows up on both sides of the equation, which means our conjugates technically show up on both sides of the equation. If I ask you which of these is the conjugate base, there are some people who interpret which is the conjugate base by anything that is a base. Both of those are base species. I completely disagree with that statement. That befuddles and confuses the whole process. Okay? But there are some that seem to think that is the case. Okay? I would prefer you to clarify and say your conjugates are only the products. The products show up only on the right-hand side of the equation. Okay. Our reactants are only acids and bases, not conjugates, and they only show up on the left side or the reactant side of the equation. Okay. Why does this even come up? Why are we even concerned about looking at these reverse reactions? Okay, so there's all our conjugates. You can look at that later. Comes back to the meaning of the double arrow. Okay? This is in reference to something known as equilibrium. All reactions have a reversible aspect to them. Okay? Which means when we look at a reaction, it doesn't just go from reactants to products. As soon as I form some products, those products can do what? Go back and form the reactants again. Okay? But when we set up a reaction, under most circumstances, we only see the forward direction. Okay? We almost always see only the forward direction. And in 130, that's pretty much exclusively what you see. In 151, that's almost exclusively what you see. This reversibility concept really only shows up in 152. In 152, you cover 8 chapters of your textbook. Of those 8 chapters, how many are on equilibrium? 5 of them. Okay. It is a complex concept. Okay. It requires lots of calculations and mathematics trying to manipulate and understand what's going on with that. Okay. So what we're going to try and do is look at the overall picture here, which, and I'm trying to preface this so you understand, this is a confusing topic. That's why there's 5 chapters on it. But what we're trying to do is come up with the best way we can explain it as possible. Le Chatelier is your next big concept that comes out of equilibrium. What we're saying is that our reaction will achieve a balance. At some point during the course of the reaction, the rate of the forward reaction, the amount of product being formed, will equal the rate of the reverse reaction. What does that mean happens to the concentrations of my reactants and products? Neutral, meaning they don't change. Under most circumstances, when we're looking at a reaction, we set up those reactions to drive to form just products, and there's a very small amount going the reverse reaction. Why do we want a small amount doing the opposite? It's a waste. The whole point was to make products. That's why we put 2 things together, was to see what comes out of it. If we don't get anything out of it, why did we put those 2 things together? Okay. So usually we design our experiments to produce as much product as possible, and so we can kind of put equilibrium on the back burner. But equilibrium plays an important role in a lot of everyday things, like, again, respiration. The ability for us to breathe is based off of equilibrium. Okay? Based off of how CO2 interacts with water. And in certain sections of your body, we want CO2 to be absorbed by water. Okay? Where might we want CO2 to be absorbed by water? I know this is basing on biology, which you may not have had yet. Okay? But just think about respiration. Okay, where in your blood? Your blood covers you head to toe. Okay, where do we want our blood to absorb CO2? When? All the time. Okay? So when I exhale, what am I exhaling? CO2. Interesting. If you're telling me CO2 needs to be absorbed into the bloodstream at all places, am I going to exhale CO2? No. That doesn't make sense because I'm breathing it out. It is leaving my body. So where do I want CO2 to not be absorbed by the water? In the lungs. The whole point of our respiration is to expel CO2, which means in our lungs, how much CO2 is in our water or in our blood? Very little, because it's expelled from the body. It's coming out. Right. Where might we want our blood to absorb CO2? Everywhere else. What is happening everywhere else? We're using oxygen reacting with glucose to make CO2. Your muscles are generating CO2 like crazy. What happens is that CO2 concentration goes up. Your blood becomes more and more acidic. That's not a particularly good thing. You feel burning. Okay? What does your body say do to get rid of that CO2? You exhale. You respire and push that out. So our bloodstream will absorb CO2 from our muscles and then transport that CO2 to some other location in our body where we can then ditch the CO2, our lungs. Okay. That reversibility comes into play. That is equilibrium. Okay. We have a very careful balance of how those reactions work to allow us to shift one way or another. Okay. Equilibrium is the maintaining of that constant level. Our body goes through and messes with that a little bit. That messing with process was first described by Le Chatelier. Okay. Our body goes through and changes the concentration of CO2 at different locations, which causes the equilibrium to shift one way or another. And we see Le Chatelier's principle. Right?
Is it possible, like, it's run by biology, to reverse cell death?
Theoretically, yes. Theoretically, yes. It is possible to do that. Okay. You have a lot of things to go through. So my organic students always hate it when I say theoretically. Theoretically, every experiment works the way we want it to. Does it ever actually? Probably 95% of the time it doesn't. Okay. So theoretically, we could reverse a lot of different processes. But what do we have to put in or sacrifice to get that reverse to happen? Yeah. Okay, so let's take a look at some ways that we can visualize equilibrium. Okay, so there's two common kind of pathways within this. Okay, we'll talk about let's do the two divided chambers first. Okay. So what we've got is our reactants and our products. Okay, two sides of a chamber. What we're going to go through and do is put in a barrier at the bottom temporarily. So we now have a barrier so it can't pass between. What I'm now going to do is dump in a bunch of reactants. Fill up the reactant chamber. Okay, and by doing so, what I'm effectively doing is just mixing my reactants with each other. But I'm telling them, you cannot react yet. Can't make products. Just sit next to each other nicely and don't do anything. Okay. I now, at that instant, say, okay, now you can react. And by doing so, I'm going to erase that barrier to forming products. So what we've now done is put in a liquid, okay, into our reactant chamber. What is that liquid going to do? Okay, it's going to fall and do what? It's going to rise up on the product side. Where is it going to stop? When both sides are equal. Does that mean reactants are not going over to the product side? No. I do have reactants moving over there. But I also have products moving over the other direction. They are moving over at an equal rate, which is why it levels out and we don't see it jumping up and down. Okay? It's moved and we now have an equal rate. That is what equilibrium is looking at. Okay? So we've set up our reaction, we put our reactants in, we said, okay, now you can react, go ahead and go. It has now reached an equilibrium state. Okay. Le Chatelier now says, okay, you've reached equilibrium, so let's pause, put in that barrier again, and Le Chatelier now said, okay, let's mess with it. Put in more reactants. Now I'm going to say reaction go. What happens? This level is going to drop and this one's going to rise until what happens? I achieve a new balance. I didn't want to erase that one all the way through. Okay. That new balance is now my new equilibrium. But here's the interesting question that comes out of it. Our initial one had those two spaces. What was the relationship between the amount of reactants initially and the amount of products initially? They were the same. In our second situation, we added more reactants, which then formed more products. What is the relationship between our new equilibrium, the concentrations of our reactants and products? What was it? They're the same. They're the same again. So if I compare in my first situation the ratio of products to reactants, I said they were the same, which gives me a numerical value of 1. In my second situation, if I do that same comparison, my products to my reactants, we said they were the same, which is 1. 1 equals 1. The interesting feature of equilibrium is once we have achieved equilibrium, the ratio of products to reactants at whatever equilibrium that is, or whatever concentrations we may have started with, will always be the same. Does that mean I always have the same number of products as reactants? No. Okay, and that is a confusing concept here. How could I adjust this so that I get more products than I get reactants? Okay, and our more will represent as our height. The taller that is, the more products we have. How can I change my experiment so that when I start this up, I get a higher product column? What could I change about this? It's not an easy one.
React more reactants.
No, if I react more reactants, all that's going to end up happening is I will still achieve that same balance of reactants to products.
Use a pump, I guess, and everything, like push it down.
So we could try bringing in a pump. That's a whole separate issue. We can't artificially change the equilibrium. The equilibrium will always achieve its balance.
Change concentration.
We'll address that in a second. What's your idea?
Don't let products to go back.
So preventing products from going back, we can potentially do that. Okay, but that still doesn't change how many products we get initially.
You could have like a volume of product first and put some in there.
If I start with some product, this is only going to drop, and that'll go up by less because there's no product there. Science doesn't do what you want, change it. What's going to happen now? The reactants will push down, and it's now not going to even out at exactly the same area. It'll go a little higher. But it can't do that, right? You put a straw into your liquid, where's the level of liquid in the straw? Just a hair higher than the liquid everywhere else. Okay. So by changing the size, if you will, of our reactant or product dimensions, we can change how much reactant or product we end up getting out of our reaction. With this two divided chambers things, it's not super obvious. So when we move to the seesaw, I think it becomes a little bit more clear. But go ahead.
Do we actually get more product, or do we just get a taller?
So this is where you have to be careful and avoid your comparisons back to physical reality. This is a model of what we're seeing. That's why I said the height we'll say is our product concentration. Okay. So what happens, let's do one more example here. Say we achieved our equilibrium. So one option we went through and did is we added more reactants. Okay. By adding more reactants, it balanced out where some more products formed. What else could we potentially do to change this? What if I scoop some reactants out? Now what happens when I remove that barrier? They balance out again in what way? Product flows into the reactant. What happens to the amount of product I get? I get less. Okay. I don't always have to add reactant. I can do anything I want potentially on each of these sides. Okay. Another suggestion was let's remove product. So as it's formed, we remove some product. Now what happens when we tell the reaction to go? it balances out again. Our reactants go down, our products go up until we've achieved our equilibrium. We could then close off the reaction, isolate our products. We can do the same thing again, okay, until we've entirely removed all of the products and all of our reactants have converted across. So what we're doing is taking advantage of that natural flow to balance out our reactants and products. It's a fascinating concept if you can ever figure it out. Okay. So let's take a look at the seesaw, because I think the seesaw to me is a little bit easier to understand. Let's put our fulcrum, which is our triangle, right in the middle. Put my reactants on that side. Okay. If I just have reactants, what happens with my seesaw? Boom. Falls off axis, and we'd have this giant angle on it. Okay. Well, the reaction says I want to strive for neutrality. I want it to be equal on both sides. So what does our reaction do? What do you mean it makes products? So we just draw, oh, here's products.
And now the reactants lose some of the least split into product.
The reaction comes along and says, okay, I need to balance this out so that I'm completely even. So what I'm going to do is take half of my reactants, turn them into products. Now what happens? Now it's evened out. So when we're looking at equilibrium, what it's doing is causing the reaction to occur to achieve this balance between our reactants and products. And if we're in a perfect situation like we are here, where it's centered, we get equal concentrations of reactants and products on both sides. And we'd end up with an equilibrium constant of 1. Okay? It's a constant because it doesn't matter how many reactants or products I put in, it will always achieve that balance. I'm always achieving a balance where this value here is my reaction constant. Okay, this is my constant, saying I have to achieve this even balance on both sides. Okay. What happens if now that our reaction has achieved that balance? Okay, so our reaction came along after we started it, achieved its balance, it's now at equilibrium, it's happy. Okay, but I want more product, damn it. Shouldn't have said that. How can I make sure I get more product? What could I do? What's that? But a reaction will always have a constant fulcrum. The fulcrum will never move for any given reaction. So this is one of the things that's interesting about it being constant. Once I've picked a reaction, the fulcrum stays constant. If I still want more products, what can I do?
Make a filter so the products can't go back to reactants.
You're making it more and more complex, but you're right, that does work.
You can put in less reactants.
If I put in less reactants, I'm just going to get less products. It's now achieved equilibrium where I have my products. What can I do? How can I get it to shift so I get more products?
Add more reactants.
What happens when I add more reactants? It's now out of equilibrium. Reaction goes, oh crap, you messed with me, I now need to fix it. What does it do to fix it? The reaction takes that half, dumps it over here. And it now achieves a new equilibrium. But the nice thing about this new equilibrium, what happened to my amount of products? It went up. I've increased the amount of products that I've obtained out of the reaction. So if I dump in more reactants, and officially just more of one reactant, I can cause it to shift. Notice that in the shift, once I've achieved equilibrium, what's the relationship between products and reactants? It's 1-to-1. It is constant. It will always achieve that constant. Doesn't matter what I do to change the reaction conditions, I will always achieve that balance. Okay? Because for any given reaction, it is constant. There's one more thing that we can do to get more products, which you started to allude to. You said prevent the reverse reaction. All right, well, by preventing the reverse reaction, let's go through and say the only way we can prevent it is if there's no products there. So it's achieved its equilibrium. It's all nice and happy now. Now I say, okay, I'm going to mess with it. And I'm going to mess with it by removing products. So I'm just going to completely remove those products. They are now no longer present. What happens to the reaction? It's now out of equilibrium. The reaction says, oh, I need to go through and fix it. Imagine it like a little automatic robot saying, oh, I need to fix whatever you're messing up. Okay. So what does it do? It'll grab those reactants, shift them over to the other side, and I now have more products. It's now re-achieved its equilibrium. If I want still more products, what could I do? Take the products off again. Now the reaction goes, oh crap, I'm out of balance again, so what do? And it re-achieves. So what can I do if I want more products? Take it off again. Eventually what ends up happening? How much product do I end up getting for each of these removals? Less and less and less, until eventually I say, this is boring, I'm going to stop pulling it out because I'm not getting enough product out of it. Okay. The other thing that we can attempt to do is change the reaction. So in this case, we've said our reaction stays constant. As long as the reaction stays constant, the fulcrum does not move. If I want more product, I can change the reaction. So by changing the reaction, I'm now going to change where the fulcrum lies. So let's just say we start with that. And I now want to change the location of that fulcrum, that triangle. Where do I want to place it so that I get the most amount of product possible? If I put it on the reactant side, what happens now? The product will go down. To re-achieve equilibrium, what do we have to do? To get it to balance, what do we have to do? We'll have to move these products over to this side to balance it out. That whole physics fulcrum arm junk. Okay? And you thought physics would never happen in chemistry. So where do we want that fulcrum to be in an ideal situation? Closer to the product side. So now what happens? By changing the reaction conditions, what do our reaction now want to go through and do? It's going to take a larger chunk of the reactants and dump them over on the product side to achieve that balance. So if we have some information about our reaction, we can then predict something about the success of the experiment. So for instance, whoa, that was supposed to be an eraser. So for instance, if we started an experiment, okay, and we knew that our fulcrum, our rate constant, or our equilibrium constant was somewhere over here, is that a good experiment for us to go through and do? No, why not? I'm going to mix my reactants and I'm going to get reactants. That's about all I'm going to get. Okay? Very little product is going to come out of that because I need a very small amount of product, small amount of pressure on that side to counter out a larger mass on the other. Okay? So if I have that information, I can say this reaction is dumb, I don't want to do it. If I have the information, on the other hand, that my fulcrum is way over here, what does that mean? I can put in a very small amount of reactants, and that small amount of reactants will turn into a comparatively larger amount of products. Even under this circumstance, though, if we go through and look at what we were talking about, the ratio of products to reactants, what would I expect for the size of that number? My products over my reactants. What should that number be? Very big, very small? It can't be just one because are those boxes equal to each other? No. If I take my product concentration and divide it by the reactant concentration, it should be very, very large. It should be a big, big number. I don't know why G's need a double line there, but they do. Crap, I should stop playing with it. Okay. I would expect a very large value. What happens if I go through and add more reactants? I'm going to get more products. What is the new relationship now? It's exactly the same. Every single time. Which is bizarre, but that's the way it works. Our reaction is dependent on this equilibrium relationship, and what we found is that it's going to strive for that neutral ground. It will always do it. Even if I mess with one side or the other, it's still going to achieve an equilibrium or a neutral state where it is completely balanced out. The relationship between my products and reactants will always be identical. I can change the product, but by increasing the product value, what must I do to the reactant value? I have to decrease it. Or sorry, increase it so that it balances out. Okay? So it's a neat little concept happening within equilibrium. Ultimately, what you need to remember is the second term of equilibrium. It is an equilibrium constant. Okay? What is special about constants? They don't change. Okay? So if we looked at acids, say like HCl versus acetic acid, which one, I give you concentrated hydrochloric acid, concentrated acetic acid. Okay? And I know I'm not a fan of torture, but it works for demonstrating abilities in this case. You're now forced to stick your hand in one of those. Which one do you stick your hand in? Hydrochloric acid or vinegar? Vinegar. Why? Okay. You've already have this preconceived notion that vinegar isn't going to hurt you quite as bad. And yet, if we add them both to water, we're going to get H plus and C2H3O2 in one case. And in the other case, we're going to get H plus and Cl minus. So why do you not care to put your hand, or care about putting your hand in vinegar, but you do care about putting it in HCl? What's different about the two?
One's harmless.
Why is one harmless? That's what we're getting at. What is the reactive species in both cases? The hydrogen. So one assumption we might go through and say is, well, clearly chloride ion is incredibly dangerous. Okay? And while emotionally we may agree with that statement, if we take sodium chloride and add it to water, we end up with sodium ions and chloride ions. So if you don't want to stick your hand in HCl, you certainly don't want to cry because your face is going to melt off. Okay? So it can't be chloride ions is dangerous. It's the H+. But both HCl and acetic acid give you H+. Why do you not care about the acetic acid, but you do care about the HCl? There's more hydrogen ion in the HCl. Why? With a very subtle change, we can show this information. The acetic acid reaction is reversible. HCl, not so much. Why is that important? In acetic acid, I form some H+, but then it immediately reacts and goes back to acetic acid. Do I have H+ anymore? No. Okay. Why does it do that? Because of where the fulcrum, our equilibrium, is established for that individual reaction. We've changed the reaction. One case it's HCl, one case it's acetic acid. Acetic acid's equilibrium is set up in such a way, and of course I drew them on the wrong side, that it matches this fulcrum. This is our acetic acid, which says what? Once I've achieved equilibrium, what is my concentration of products? Relatively low in comparison to my reactants. which means if my products are the one that generate H+, I have a very tiny concentration of the H+. If I go through and look at HCl, what's happening with HCl? I have a very tiny amount of the HCl and a massive amount of H+. What is causing that burning? The H+. Because we've changed the reaction, the equilibrium, our fulcrum on our seesaw has changed positions, which now means we're going to see different results come out of it. In one case, we see a very small amount of acetic acid. In the other case, we see a very small amount of H+ in the case of our acetic acid. And in the other case, we see a massive amount of H+ with the hydrochloric acid. Both of them are acids, but they have different equilibriums. That difference in equilibrium makes a dramatic effect on the safety of each of those individual chemicals. Okay? Which then brings us to the next issue. You cared about hydrochloric acid, but you didn't care about vinegar or acetic acid. They're both acids. In one case, you've already intuitively brought into your head that HCl gives you a lot of danger, acetic acid gives you a minimal amount of danger. We now have some way to sort of quantify that. Okay. We can now subcategorize this because we now have ways to differentiate between them. We, of course, need to go through and name them. Hydrochloric acid we will reference as being a strong acid. And as it being a strong acid, it generates lots of H+. Acetic acid is a weak acid, and so it generates very small amounts of H+. Okay, skip over that. Okay, so we now have to approach what these definitions are. Strong acids completely ionize in water, which means when I add HCl to water, all of that HCl becomes H+. Weak acids only partially ionize, meaning when I add acetic acid to water, only a small amount of it converts to H+. Most of it stays as acetic acid. Okay. Well, you already knew your strong acid, and you knew acetic acid was a weak acid. How did you know that? Prior knowledge. How are you going to know it in the future? Prior knowledge, unfortunately. You are told to memorize your strong acids versus your weak acids. So if I give you HBr, you need to be able to tell me that that is a strong acid or a weak acid. Which is it?
Strong.
How do you know it's strong?
Prior knowledge.
What is your prior knowledge?
Writing down strong acids.
Strong or weak? Strong or weak? Very hard to tell the difference between strong and weak. The definitions that we've got are technically true, but the only way you would be able to figure those out is by going into the lab and testing them. That's a bit of a silly way to test them. You could also stick your hand in them. Also, not generally a good idea for figuring it out. What your prior knowledge is going to be is that you need to memorize what the strong acids are. Okay? Again, more relevant as you move into 151, but that's what you're going to be expected to do. Your strong acids are defined here: HClO4, H2SO4, HI, HBr, HCl, and HNO3. Okay. It is, what is that, 6? Pretty sure there's supposed to be 7, but those are the 6 most common ones. You are expected to know that those are strong acids. Well, how would you know what a weak acid is then? It's not one of those that you're told to memorize. So your weak acids will just be everything else. If we look at our strong bases, what do our strong bases all have in common? OH, OH, OH. For those of you in lab on Tuesday, You want to expand on that? Is it really just OH? What was it? That's going to be our signifier for seeing it. No. So lab on Monday, hold your tongue for a moment. Strong base, weak base. Ready for the answer? Trick question. It's not an acid or a base. Are we looking for OH? No. We are not looking for OH. So what Amber was suggesting was OH bound to a metal. Okay, that helps in identifying that you have a base. Okay. Why? Why is bonding OH to a metal so drastically different than bonding OH to a nonmetal? An ionic bond. What does the ionic bond have anything to do with it? It is a metal and a nonmetal, so we'd end up with OH ion in the ionic compound. In the covalent compound, we don't have OH ion. What we are looking for is not OH, but the anion form of OH, also known as, maybe it'll help if we draw it out here real quickly. One of the anions you are responsible for knowing?
Hydroxide.
Hydroxide. The presence of hydroxide is what's triggering our strong base alert. We do not have hydroxide in that bottom situation because that oxygen is bound to the carbon. They share electrons, which means we don't have OH minus. We don't have hydroxide in that situation. Okay? So it's recognizing what pieces are important to look for versus in other situations. Okay? Should always be considering safety. So we said our important aspect is the amount of H plus present. So we could go through and reference this for little Jimmy. Watch out for that 0.15 molar H plus solution. Why? Well, 0.15 molar tells us the concentration of H plus in that solution. So all we have to teach Jimmy about is now not only numbers and decimals, but now the mole concept and volume and what H plus was. Okay. Well, Jimmy's a smart little boy. He can deal with it. Okay. When did you guys all learn about those concepts? Just now. Okay, so maybe that's not a good thing to be teaching little Jimmy because he's going to get lost in all those numbers and confusion. So maybe we want a different way that we can tell somebody that hasn't taken this class, watch out for that solution because that's not a particularly safe one. Okay? What do we use? We use a system known as our pH. Okay? How is that helpful for us? What the pH does is it converts our concentration of H plus into a number between 1 and 14. Most of us can deal with numbers between 1 and 14 because we've got at least 20 digits. Okay, which may sound dumb, but that's fair. I mean, we should really be honest with ourselves. Okay? So now we can tell Jimmy, watch out for that solution because if you stick your hand in it, it's a pH of 0, you're going to end up with 0 fingers and toes. Doesn't quite work on the opposite end. Don't stick your hand in that solution at pH 14 because you'll end up with 14 fingers and toes. Okay? But it at least covers the acid side of it, which is important because if you were told, watch out for that acid solution versus watch out for that base solution, which one do you avoid instinctively? The acid. Why? 0 fingers and toes. Are bases equally dangerous? Absolutely. Okay? But for some reason, we've decided as a society that we don't care about the bases, we only care about the acids. Okay? So it's much easier to teach our kids these things or people that haven't taken a science class. A low and a high pH are both bad. The low pH corresponds to an acid. A high pH corresponds to a base. Which means when we look at solutions, what are we trying to aim for? We don't want the low end. We don't want the high end. We want the middle, our kind of equilibrium, if you will, end of our spectrum, and we're aiming for pHs around 7. Okay? This allows us to interpret and present data quicker and easier and more effectively than other situations. The last thing that I'll mention is how do we calculate pH. This is what all 150 students love to talk about. It is a representation of the concentration of H+. Concentration is written with a bracket. We take the negative log of the concentration. What is a log? Ask your math teacher. It's the little button on your calculator. You push the log, you put a negative symbol in front of it, and it spits out a number. That number will be between 0 and 14. Okay?
Wait, sorry, can you go back like 2 seconds?
Yeah, I'll go back 1 second, and then I'm